Lesson number 5 is graph of rational functions. So what we're going to look at in this section is there a way that we can possibly sketch the graph of a rational function without having to rely on the graphing calculator? So just a couple of points of review. If a rational function has a denominator that can be made equal to 0, then the graph will have a vertical asymptote or a point of discontinuity corresponding to the 0 of each of the denominators. So if I have a rational function f of x, which is n of x numerator over d of x denominator, if n and d have no common factors, we get vertical asymptotes and horizontal asymptotes. Vertical asymptotes we can calculate algebraically by finding the zeros of the denominator, because the zeros of the denominator are the non-permissible values, which I cannot have, which creates my asymptotes. The horizontal asymptotes, we look at the degree of the functions. So if the degree of the numerator is less than the degree of the denominator, the x-axis or line y equals 0 is the horizontal asymptote. If the degrees are equal to each other, then the line a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator, becomes the asymptote. So that example we looked at yesterday, on the right-hand part of the graph, there was no asymptote, but on the left-hand part, there was an asymptote of 1/2. And then if the degree of the top is greater than the degree of the bottom, there is no horizontal asymptote. Then we have points of discontinuity. Points of discontinuity occur where we have common factors. And usually what ends up happening is those common factors cancel things out in the denominator, which affects my non-permissible values. So in that point of discontinuity, there's a break in the graph, and we designate that by an open circle. So to find a point of discontinuity, we factor the rational expression, we simplify it by canceling out the common factors, and then we substitute in any non-permissible values of x into that simplified equation. And that gives us the point of discontinuity. So if we look at the first set of graphs that have no discontinuity, if the denominator of a rational function has no zeros, there will be no discontinuities. So the type of function that is not going to give us permissible values are functions where the x value is squared, or to the power of 4, or to the power of 6. Anything that no matter whether x is positive or negative, I can never get a negative value. So in this one right here, if x is -9, when I square it, I get a positive 81. That's not the only thing though. The next thing that we have to add is I'm adding 1. So I'm always making it even more positive. So in this case here, when x equals 0, I get 0 plus 1. I still get a value, an allowable value for x. So if we answer these questions, does the function have any non-permissible values? The answer is no. All values are actually permissible, which means the domain of this function would be that x can be an element of the real number system. Now it says the maximum value of the function will occur when the denominator has its lowest value. So what will be the maximum value of this equation? Well, if x equals 0, f of x will equal 1 over 1, or just 1. If I let x be equal to 1, I'm going to get 1/2, which is smaller than 1. If x equals 2, I'm going to get 1 over 5, which again is smaller than 1. If I let x be equal to -2, I'm still going to get a positive 4. So this remains as its maximum value. Explain why the value of f of x can never be negative. Because for all values of x, x squared is positive, and then add 1 is still positive. function have any zeros? No. There's never a zero, because a zero would imply that I get, when f of x, when x equals a value, I get 0 for an answer, and that does not happen. So question F says, use the above answers to suggest a possible range for the function. So I can't get any zeros, which means y can never be equal to 0, but y could possibly be anything else except for right here, I have a maximum value. So I have that x can never be 0, or sorry, y. Y can never be 0, y can never be negative, but the maximum that y is going to be is 1. So that gives me a range where y is such that, y is going to be between 0 and 1. And it can be any value between 0 and 1. So it could be an irrational number as long as that irrational number had a value between 0 and 1. So now if we use the graphing calculator to sketch this graph, we're given a window setting to use. There we go. So my window settings are going from negative, -7 to +7, going up by 1s, and -1 to 2, going up by 1s. So my y equals is going to be 1 divided by, and then bracket, x squared plus 1. And so when I graph this, I get this graph that really, it looks like a hill. It's symmetrical on both sides, reaches this maximum point of 1, and never touches the x-axis. So it makes the graph look like this. Now, does this graph look to have a vertical asymptote? No, because the graph just keeps approaching. There's no limit going vertically that the graph does not touch. Plus, in order to have a vertical asymptote, I have to have a denominator that would be equal to 0, which does not happen. Because my denominator never equals 0, I no longer have a point of discontinuity. Plus, I don't have common factors for the numerator or the denominator. So no vertical asymptote because d of x never equals 0. Do I have a horizontal asymptote? Yes, I do. And it's the y-axis, or sorry, the x-axis, which is the equation y equals 0, which still follows our rule. The degree of the top was 0, and the degree of the bottom was 2. So it still follows that rule where if the degree of the numerator is less than the denominator, the x-axis becomes my asymptote. So in section 2, it says graphing calculator screenshots of 4 rational functions are shown using the following window settings. So what you are asked to do is to answer the following questions. So finding the horizontal asymptote, if any exists, of each graph. Do the equations in the first one agree for the rules? And explain as x approaches positive or negative infinity what happens to some of the graphs. So I'm going to give you a couple of minutes. What I would like you to do is pause and then continue playing so that to see if you can answer some of these questions on your own. Okay. So if I look at question A, the horizontal asymptote of each graph. So if I look at this one, the horizontal asymptote, yes, does look to be the x-axis. So that would be the equation y equals 0. Now, if I look at question 2, that is very similar to kind of the question that we were looking at yesterday. And that part of the graph kind of looked like it had an asymptote, but part of it didn't. So if I could erase this part of the graph and say that that part of the graph does not exist, do I have an asymptote? Well, this goes up and it appears to be coming down. This comes down and goes up. And what pattern do we see? We see a pattern of it approaching the x-axis again, which again would be an asymptote of y equals 0. So when we are looking at a horizontal asymptote, that horizontal asymptote does not need to be the entire graph. It could be a section of the graph. So in this case here, even though the graph goes through 0 here, it does not actually, in this part here, it approaches 0, which is what makes it the horizontal asymptote. It approaches 0. If we look at I, do I look to have a horizontal asymptote? Right there, which would be the equation y equals 1. And then for number 4, k of x, does it look like I have a horizontal asymptote? No, because this just keeps getting higher and higher. This gets lower and lower. So it does differ from this equation, or from this graph. So this last one has no horizontal asymptote. So question B says, do the equations in part A agree with the rules? So the rules being the degree. So if I look at the degree here, the degree of the top is less than the bottom, x-axis, yes. The degree of the top is less than the bottom, x-axis, y equals 0. The degrees are the same, so it's leading coefficient, 1 divided by 1, which is 1. And in this last one, the degree of the top is greater than the bottom, no horizontal asymptote. So do they agree? Yes, they do. So question C says, explain why as the value of x approaches positive infinity, the graph of x over x squared plus 1 approaches y equals 0 from above, but as it is negative, it approaches it from below. So let's start with this one. Why is it as the value of x gets larger and larger, the graph is going to be a positive value getting close to 0? Well, if I imagine a really large number, like even 1,000, this is going to be 1,000 over 1,000 squared, which is 100,000 plus 1, so 100,001. When I divide this, I get an incredibly small number, but it's still a positive small number. Because as x approaches infinity, the numerator and denominator are positive. When I look at the x value approaching negative infinity, the numerator is negative and the denominator is positive, which means g of x will be negative, which is why it will approach from below, because the value of g of x is going to be negative. Question D says, explain why the graph h of x has no points in quadrants 3 and 4. So why does this graph not exist down here? Well, because for all negative x values, when I square them, I get a positive value. And when x is positive, it remains value. or it remains positive. So the explanation that we could put is for all values of x, for all values of x, h of x is positive, which puts it in quadrants 1 and 2. So class example number 1 says consider the following functions. So it says without sketching the graph, determine which of the followings have no discontinuity, a vertical, a horizontal, where the x-axis is horizontal, where I have a point of discontinuity, or the horizontal asymptote is the line y equals 1. So before you answer this question, the first thing that you're going to need to do is go through each of these functions from A through J and factor them. So pause this, take some time, factor them, and then turn this back on so that you can see as we go through each of the factors. Okay, so if I look at A cannot be factored. If I look at B, I can factor the top because it's a difference of squares, but it doesn't allow me to cancel anything with the numerator, or with the denominator. If I look at C of x, I can factor the bottom, but it doesn't allow me to cancel out any common factors. In D of x, I now finally have my first common factor, which means I get 1 over x minus 2. So I have a common factor that I can cancel. If I look at E, I cannot factor x squared plus 4, so it is in its simplified form. If I look at f of x, x squared plus 4 over x plus 2, x minus 2. G, I have these negatives to contend with. So if I remove the negative in front of the x, that's like factoring out a negative 1. So then I get x plus 4. Do the same thing on the bottom, factor out a negative 1, and I get x squared plus 4. These negatives actually cancel each other out. Negative 1 divided by negative 1 is positive. So then I get x plus 4 over x squared plus 4. I can do the same thing to h of x. I can factor out this negative 1. Factor out a negative 1. The negative 1s will cancel out. So I'll be left with x squared plus 4 on the top. And this x squared minus 4 on the bottom can become x plus 2 and x minus 2. With I, x plus 2 times x minus 2 over x plus 2, and I'm left with x minus 2 as a result, because again, I had common factors. And with the last one, I can factor out an x squared, and I'm left with x minus 4. I can factor out an x on the bottom, which leaves me with x minus 2. I'm going to be able to cancel one of the x's out. So I'll get x times x minus 4 over x minus 2. So we've now factored all of these. If I go through, the one thing that I probably do want to write in on these ones that I did some canceling is I still have in here x can equal negative 2 because of this 0 right here. Or in this one again, x cannot equal negative 2. In this one, I canceled out an x, which means that, oops, there should be a comma, x cannot equal 0. Try that again. X can't equal 0. So, which of these graphs have no discontinuities? So in other words, look at the denominators. Which ones have denominators that no matter what value of x, they're always going to be positive? And the answer to that would be B and G. Because I've got an x squared, which will always be positive, and then I'm adding even more positive to it. So that will be B and G. Which of the following will have no vertical asymptotes? When do I not get a vertical asymptote? I don't get a vertical asymptote when I have the bottom always being a value. So when I can always, no matter what the value of x is, I can always get a value for the denominator. So that would be B and G again. And there is one other one. And that last one would be I, because I have no denominator in its simplified form. I do still have a restriction, but that restriction does not give me an asymptote. Question C, which of the following have no horizontal asymptotes? No horizontal asymptotes happen when the degree of the numerator is bigger than the denominator. So where did we have a circumstance where the degree of the top was bigger than the degree of the bottom? The first one that we have is right here, E. Then we have it again in I and in J. D says which the following is the x-axis a horizontal asymptote? The x-axis is a horizontal asymptote when the degree is less. So when the numerator is less than the denominator. So when does that happen? Equal, equal, less. So there's C. Less for D. Greater, equal, less. So G. Equal, more, and more. So C, D, and G. Question E says, when is the horizontal asymptote going to be y equals 1? Well, that's when the degrees are going to be equal to each other, because that's the only time that I can get an asymptote, a horizontal asymptote, other than 0. And in order for it to be equal to 1, that means that A over B has to be equal to 1. So the leading coefficients would have to be the same. So when is it equal? It's equal at A. The leading coefficients are the same, so I'm going to have y equals 1. In this one, they're also both the same degree, too. Leading coefficients are the same, so that would give me the equation y equals 1. C is no, D is no, E is no, F. The degrees are the same. Leading coefficients are the same, so I will get the equation y equals 1. And H, the degrees are the same, and the leading coefficients are both negative 1s. So that also gives me y equals 1. And then F is points of discontinuity. So a point of discontinuity happens wherever we have common factors. So where did we have factors that we canceled out? D, I, and J. So D, I, and J would be the answer to that part. Last example. Algebraically determine the equations of any asymptotes and the coordinates of any points of discontinuity on the graph of the following function. State the domain and the range of f. So if I look at this, in order to continue on, in order to determine those vertical asymptotes, I want to factor the denominator. So when I go to factor the denominator, two numbers that multiply to negative 15 and add to negative 2 would be negative 5 and positive 3. So negative 5 and positive 3 now give me non-permissible values. X cannot be equal to negative 3 and positive 5. I also have common factors that I can cancel out. So I now get this new function, f of x equals 2x minus 1 over x plus 3, but x cannot equal negative 3 or 5. So now we look at our asymptotes. Our horizontal asymptote, we look at the degrees. This, if I expand this out, is a second degree function. 2x squared minus 11x plus 5. Degrees are the same, which means that the horizontal asymptote is going to be the equation y equals a over b, which will be 2 over 1, or 2. So the horizontal asymptote will be y equals 2. Then, because I had a common factor, I have a point of discontinuity. The point of discontinuity I get by taking that 0, which was 5, and putting it into the simplified equation. So 2 times 5, which is 10 minus 1 is 9, over 5 plus 3, which is 8. So the point of discontinuity would be at the point 5 and 9/8. And then I have this non-permissible value that x cannot equal negative 3. That gives me a vertical asymptote. X is equal to negative 3. That becomes my vertical asymptote. So now if I look at my domain and my range, my domain is the easier one because it's the non-permissible values. X cannot equal negative 3 or 5, but x could be anything else. And then for my range, I have that x will never equal 9/8 because that's the y coordinate of my point of discontinuity. And y can't equal 2. That's my horizontal asymptote. So the set of y values such that y cannot equal 9/8 or 2, but it could be y. It could be anything else. So this section really explored the idea of horizontal and vertical asymptotes and points of discontinuity. So the questions that I would like you to practice on, questions 1, A, D, and E for